Hello and welcome everybody to this lecture on computer architecture. I want to take a look again at the number conversions because we didn't quite finish this yet, or maybe let's say it like this, let's put another look at this. And the first thing I want to do is to say that we are very familiar with base 10 calculations, and that is why if we can do the calculations in base 10 then the things are quite easy. So let's take a look at this example before from last time. We had 1, 2, 3, 4, 5, base 6, and we want to know what it is in base 10. So what we basically do is just a multiplication. And to help this multiplication, I've made here a series of 6 powers. So the 6 to the power 0 is 1, 6 to the power 1 is 6, 6 to the power 2 is 36, and all the way up to 6 to the power 5, which is 7,776. And then what we're doing, we're making a calculation with the help of a multiplication table that we've all learned in primary school. I hope so, at least, which is represented here. This one we will talk about in a moment. But what we're then doing is 1, 2, 3, 4, 5 in the hexal system is 5 times 1 plus 4 times 6 plus 3 times 36, which is 108, plus 2 times 216, which we get here from the table, and this is 432, and 1 times 6 to the power 4, which is 1296. And then we do the addition, and with the addition we get this carries and things like this. I'm sure you're familiar with how to do adding and multiplication in decimal. So 1, 2, 3, 4, 5 in the hexal system is 1865 or 1865 in the decimal system. If we want to do it in another way, it can also be done. Instead of multiplications and adding, what we can do is actually divisions and subtractions, and that is done in the source system. And that is much more complicated because we are not familiar with doing calculations in the source system, in this case hexal. But let me show you how this looks, how this works, and it's quite complicated, so follow me. 1, 2, 3, 4, 5 in the hexal system, we divide by 10 in the hexal system, which is 1, 4. 1 times 6 plus 4 times 1. If we were familiar with this, then just pause the video. You can do this, but it's quite complicated. We will get that this is 510. That is 5 times 36 plus 1 times 6 plus 0 times 1. And we have a remainder of 5, which is still to be divided by 10, which is 1, 4 in the hexal system. So the remainder is 5 in the decimal system, which we have to remember. Then we continue with the integer number. 510 divided by 14 is 30 in the hexal system, and we have a remainder of 10 in the hexal system, still to be divided by 14 in the hexal system. So we have a remainder of 10, and that we remember in the decimal system, which is 6. So far so good. 30, we continue with the integer. 30 divided by 14 is 1, with the remainder of 12, which is 8 in the decimal system. And then finally 1 divided by 14 is 0, with a remainder of 1, and this 1 we also remember in the decimal system. And now we can read here back to front 1865, which is the converted number in decimal. Just rewind this video and place it again to if you don't understand it, or just do it on paper. The calculation is very difficult. And we have converted from 6, the hexal system, to the decimal system, which is 14 in the hexal system. And that is done by divisions and subtractions, because we are subtracting this part here, the remainders. Now, considering that we are acquainted very well with the base 10 calculations, conversions from base 10 to other bases are better done with the latter technique, with divisions and subtractions, while conversions to base 10 are easier done with the former method, which we shown on the previous page. Conversions from base x to base y, with both of them not being 10, can also be done by first converting to base 10, and then from base 10 to base y. That's just a remainder, but you will probably not do this very often. Very often you will just do from binary to decimal and from decimal to binary. Finally, also here I want to point out that if you have floating point, so you have something like 0.1825 in decimal, and you want to convert that after the floating point, then you do the opposite operations. So you multiply and then subtract. So to give you an example, 0.8125, and we want to convert this decimal number, floating point number, to a binary floating point number. We multiply by 2, so we get 1 plus 0.625. So we remember this 1 and we continue with the rest. And that is 0.625 multiplied by 2, we get 1 plus 0.25. We subtract this 1 and continue with the rest. So that is 0.25 multiplied by 2, we get 0 plus 0.5. And then we go on, 0.5 multiplied by 2, and that is 1 with a sum of 0.0, and we are ready. So now we can read the number from here to here, and we get that 0.8125 is 0.1101 in binary. Note that this conversion doesn't always work. Sometimes this series can be infinite. But that is basically how conversions are done. We can either do it from the destination system, or we can do it to the destination system. And whatever is more convenient, of course, we are going to do. And of course, the calculations in binary are very simple because the multiplication table is very simple, as I've shown here on the right, which is just 0, 0, 0, 1. And that is why the computer can do this very well. And to show you once again what we're doing from decimal, as an example, decimal to binary, well, decimal is the one we like. So what we're going to do, we're going to do divisions by 2 because it's binary, and then remove constantly the remainder. So 234 in decimal, what is it in binary? We divide by 2, it's 170 plus a remainder of 0. So we continue with 117 and divide by 2, which is 58, plus a remainder of 1, and that is 58 is 29 without remainder. 29 divided by 2 is 14 with a remainder of 1, and then we get 7, 3, etc. And now we read at the end, we read the number backwards, so we get the binary 234 in decimal is in binary 1, 1, 0, 1, 0, 1, 0. And if you want to convert this number 11101010 to decimal, of course we use the opposite technique. We multiply this with 1, this with 2, this with 4, this with 8, this here with 32, 64 and 128, and we get of course 234. So this is basically how it works. I want to show you one more funny thing, that you can actually have numbers in a unary system, base 1, and in a unary system digits only have one possibility, namely 0. If you want to express 7 base 10 in unary number, it is just 7 zeros. That is funny. Every digit has the same weight because 1 to any power is 1. So actually the number is just the number of zeros. And that is basically what we used when we count with money. This is the number of coins we have in our pocket, with every coin the same value. Maybe this is something funny and interesting that you did not expect, but I hope you enjoyed it.